You know, special relativity is one of the absolute cornerstones of modern physics. But what if I told you there wasn't just one way to get there? It turns out there are two completely different mathematical journeys that lead to the exact same world-changing conclusions. So let's dive right in and break this down.
Now, these ideas we're exploring today aren't just something we pulled out of thin air. The whole analysis is grounded in the amazing work found in Chapter 6 of the book Newton and Relativity by Sester, Clemente, and Korf. We're really just trying to bring their fascinating argument to life here.
And let's be crystal clear about something right up front. We are not here to criticize Einstein's theory. Honestly, it's incredibly elegant. That core idea that the speed of light is the same for every single observer is just a beautiful, profound insight. It proves there's no special, preferred viewpoint in the universe, not even for information itself. We're simply exploring a different road to get to that same amazing destination.
This image really captures the whole idea perfectly. You've got two routes. They both lead to the exact same place, the reality of relativity with E equals mc squared, time dilation, the whole shebang. The critical difference, as you're about to see, is that one path builds a continuous bridge from classical mechanics, so you don't have to make any big, counterintuitive leaps.
All right, so let's start with the path that most of us are probably familiar with. You can really think of it as a revolutionary leap, a clean break from the classical way of thinking.
So this journey starts with what you might call a postulate chasm. It begins with a huge assumption. The speed of light is constant for everyone. Now look, we can verify this with experiments all day long. It's true. But you can't prove it from classical mechanics. In fact, it completely contradicts it. And that creates this giant chasm between the old physics and the new.
And once you accept that one postulate, a whole chain of dominoes starts to fall. Suddenly, space and time aren't absolute anymore. The old school common sense math for adding velocities? Totally out the window. You need a whole new set of rules, the Lorentz transformations, to handle things moving super fast. And these new rules lead directly to all those famous, kind of paradoxical ideas like length contraction and time dilation. It's only then, way at the end, that the relativistic mass formula is derived as a consequence of all this.
So the key thing to get here is the structural friction of this approach. It creates this disconnect. It's a revolution, not an evolution from what came before. And that has a really high cognitive cost, you know? It forces you to accept these incredibly mind-bending, non-intuitive ideas right at the very beginning of the journey.
But what about that other path we mentioned? Let's explore how it builds a continuous classical bridge, starting from the physics we already know and understand.
This journey starts in a completely different place, deep inside classical physics. It takes the idea of mass-energy equivalence, E equals mc squared, and applies it right to Newton's second law. And from there, it shows that an object's inertia increases at high speeds not because its mass is changing, but because of the mass associated with its incredible kinetic energy. And that right there, that creates a solid, logical bridge from Newton straight to Einstein.
Okay, and this is where it gets really cool, because this method completely flips the script. Instead of starting with the idea that the speed of light is constant, this method treats it as the result. You feed in established laws, things like the conservation of energy and momentum, into the engine, and what comes out the other side is a mathematically proven principle. The speed of light has to be constant. It's not a postulate you just have to believe anymore. Okay, so we've looked at the two paths. One feels like a revolution, the other feels much more like an evolution. Let's put them side by side so we can really see the difference.
Let's just break this down point by point. The traditional method's foundation, it's an assumption, a postulate. The alternative, it's a physical principle you can derive. One is disconnected from classical mechanics, the other is totally connected. In the traditional path, the rules of motion, kinematics, end up dictating the rules of forces, mechanics. In the alternative, it's the other way around. And maybe the biggest deal of all, the speed of light goes from being the thing you have to assume at the start to being the thing you prove at the end.
Like we said, both journeys get you to the exact same destination, but the experience of that journey is profoundly different, and it's all about where the paradox shows up.
This image shows it perfectly. The traditional method starts you off with the weird stuff. Boom, absolute space and time are gone. But the alternative method starts with solid classical ideas and arrives at those exact same conclusions as undeniable mathematical necessities, but at the end of the journey. The weirdness isn't a leap of faith you take at the start, it's the inevitable destination you arrive at.
So what this alternative way of thinking really gives us is a seamless continuity. It weaves classical and relativistic physics together into one single coherent story. It restores a logical, step-by-step progression to the very foundations of how we understand our universe.
So why does all this matter? What's the big takeaway? Well, first, you get to the exact same place, the same brilliant conclusions, without needing to start with a paradoxical assumption. Second, it creates that continuous bridge, framing relativity as an evolution of classical mechanics, not some total break from it. And finally, just from a learning standpoint, it's way more elegant. It makes one of the most difficult topics in all of physics feel much more intuitive and just easier to understand.
At the end of the day, both paths lead us to the same profound truths about how our universe works. Which leaves us with a really fascinating final question to think about. Does the path we take to discover a truth change our relationship with that truth? Something to chew on.